Okay, then organic compounds. Um, any member of a large class of chemical compounds whose molecules contain carbon. Exceptions include a few types of compounds such as carbonates, simple oxides of carbon, and cyanides, as well as allotropes of carbon like diamond, that type of thing. Organic compounds are grouped into families, and have a look at that. So you've got the diversity, then you've got the single molecule, you've got bonding, then you've got chains, so you've got from the single to the poly, and you've got branched chains, you've got a group here at the side, and you've also got rings as well. And you've also got your single bonds, your double, and your treble, and this leads to different families, different names. So the carbon compounds are able to bond with many types of elements, with different types of elements, including hydrogen, oxygen, sulfur, nitrogen, and the halides, e.g. chlorine and bromine. Okay, so you've got the backbone structure, and then you've got a functional group just here, and this dictates how the molecule will react. Okay, there are aliphatic hydrocarbons and aromatic hydrocarbons. Hydrocarbons are compounds consisting of carbon and hydrogen only bonded together covalently. Hydrocarbons that consist of a straight or branched chain of carbon atoms or rings of carbon other than those containing a special aromatic ring called benzene are called aliphatic hydrocarbons. And then here's the aromatic hydrocarbon that we were just talking about, and this is kind of unique. The simplest possible aromatic hydrocarbon is benzene, and what's unique about these is the conjugated system occurs where atoms covalently bond with alternating single and multiple, e.g. double bonds. So here you've got the double, single, double, single, double. So okay, so you've got the alternating. And then some examples, further examples of aromatic hydrocarbons. And interestingly, these compounds tend to have a sweet scent. Okay, so the functional group then within a molecule is an atom that shows a characteristic set of physical and chemical properties. And so all organic molecules can be divided into families. So for example, we've got our alkanes and our alkenes and alkynes, a single bond in between, a double bond, and this should be a treble bond then here. And an example then would be ethane, ethene, and ethyne for the three different types. An example out of each of these families. And some derivatives of hydrocarbons, you've got alcohols and thiols, for instance. So simplest one is CH4 is methane, so substitute and add a functional group OH on. You've got methanol, similarly CH4, you've got an SH replace one of the H's, so methane thiol. An amine, basically almost NH3, which would be ammonia. So it's an amino group added on to the CH, what was CH4, now is CH3, and then you've got the amino group added on. An example would be methylamine. Now bonding in between the carbons, you've got an oxygen, which makes an ether, or sulfur, which is a thioether. So examples of that would be then dimethyl ether and dimethyl sulfide. That would be two examples there. The di for two of these, and CH4 being methane, so therefore we're talking about a methyl group with the CH3 there, and then you have the oxygen in between. We have two of the methyl groups, so it's dimethyl and ether. And then you've got the carbonyl group. And with carbonyl groups, you've got aldehydes and ketones then. and then carboxylic acid with derivatives of esters, amides, and acid halides, all under the carbonyl group, remember now. Okay, to draw chemical structures then, you've got the full structural formula, which has all the branches and all the bonds and the hydrogens and carbons included. Condensed structures then are these, and even with this branch here, that can be further condensed to a CH3 and this is 2-methylbutane, C5H12. Okay, the line formulae are important then. It's an abbreviated way to draw the structural formulae, this type of line formula. And basically the idea is that at each intersection you've got a carbon right there and then a hydrogen branched off that. Two hydrogens branched off, and at the terminals you've got a CH3, then a C here with 3 H's coming off it, forming the 4 bonds. Carbon and hydrogen atoms aren't usually shown. Atoms other than carbon and hydrogen are shown. That's important. Okay, so looking at this formula right here then, we have C, C, and we have 4 C's there, 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 and there. And then we have this branch coming down here, which is this branch, and it's a CH3, so that's very straightforward. Yeah, this formula right here then has a bromine branching off the second C. So we see that's clear to observe right there. So there's the C, and we've got a hydrogen off that and also a bromine. And then we've also got a CH3 there. So the CH then, there's where our CH is, and we've got a CH3 right there and a CH3 right there. So that contributes to the CH3 that we have right there. And then with our cyclic formula that we have here, basically we just draw the hexagon and no hydrogens. There's a C at each one of the corners there, and the hydrogens aren't illustrated. And some complex biomolecules, a couple of things you spot there. We've got an amino acid, so there's our amino group. We've got a carbonyl group there as well. We've got our OH there as well, and several other more complex. DNA actually, deoxyribonucleotide. And then some other molecules as well, caffeine and ibuprofen.